We should accept that. Okay, great. So it's my great pleasure to introduce today's speaker, Clement Atzberger. Clement is a professor at Goethe University in Vienna. He's been working with us, several of us actually, Maddie and Yihang already, and then he'll be working with Felipe later on the summer as the co-founder of Mantle Labs. So Clement has very great amount of experience in remote sensing. He's been teaching me a lot about this. I'm one of the students that doesn't know it. And it's really wonderful to have him here for the next 2.5 months or so. So he'll be hanging around in Maddie's office at 10:06 if you're around. And yeah, so I'm really looking forward to the talk. So it's all yours. Thank you.
Yeah, thanks. Thanks also for welcoming me, and thanks for hosting me. And my arrival was more or less smooth, except the weather
and
the train strike. But I made it, and I have a nice tiny house, so I feel well here. Yeah, thanks. So I want to talk about, let's say, a kind of niche area of remote sensing, because as you know, most people use remote sensing for kind of change detection or land cover mapping and land use change, so more in the thematic domain, right? Or they do some quantifications, but then using kind of empirical data sets. And I'm working since a long time in this field of radiative transfer modeling. So, and I think it's exciting because it allows you to do a lot of stuff, but without heavily relying on field data or empirical data. So, but just to give you a bit of my background, as Keshav said, so I have several roles. I'm a professor for remote sensing and geomatics at BOKU. You see this nice building. I think that is as old as, let's say, Cambridge University or more or less. But we don't have, let's say, real remote sensing department, because we serve mainly agricultural students or forestry students. So it's more a byproduct because they make use of remote sensing, but they don't have this as a major topic. So, and since 2016, I'm one of the co-founders of Mantle Labs. So that is very exciting because we do this global agricultural intelligence. And then a spin out of Mantle Labs is then Geotree, where we do, let's say, all this monitoring, reporting, verification for these nature-based solutions. I learned remote sensing in INRA in the 1990s. That is in France, in Avignon. And there you will understand why I touched these radiative transfer models, because they were leaders in this field. And as you know, as a student, you arrive somewhere, you are completely clueless. And the first topic you encounter that will shape the rest of your life somehow. So what is a radiative transfer model? I'm not going too much into the physics, because there's, of course, physics and mathematics behind, but it's essentially a bunch of equations describing the relation between inputs and outputs. And in the case of vegetation radiative transfer models, the outputs would be the reflectance spectra. Yeah, this is what we want to simulate. And the inputs would be, let's say, some characteristics of the objects. And you can see this also as a kind of generative model. I think that is the term which is more used in computer vision. Yeah, you generate something. But here the parameters have really physical meaning. So it's not some latent variables. Perhaps as an example, if you think about the atmosphere and you want to model the transmission of the light through the atmosphere, you can imagine there's some equation describing this, and you immediately understand, okay, I need to know the sun elevation angle, right? Because this is the path length through the atmosphere. I need to know the concentrations of the absorbers and the scatterers, I don't know, ozone or water vapor or aerosols and so on. But I need also to know some scattering coefficients. So once you have these, you can build these equations, and then if you have then the concentrations and the sun angle, you can simply calculate the transmission. So there's no need to measure it. So this would be a simple example of a radiative transfer model applied to the atmosphere, which is of course much simpler than vegetation canopy, because in the atmosphere, you know, the molecules are well mixed. Okay, there are height gradients, but let's say the gases and so on, they are well mixed. And in a vegetation canopy, you understand it's a bit more complicated because we have the leaves, right? And so it's more difficult to describe this precisely using physical relations. So a radiative transfer model for vegetation would then simulate the reflectance spectra from UV, so let's say 400 millimeters up to the sphere, or you could go beyond. You could also build a radiative transfer model for microwaves, right? There are radiative transfer models for thermal data. Whatever wavelength range you are interested in can be modeled. So we distinguish mainly three types. So in computer graphics, in the gaming industry, I believe what is most used are kind of ray tracing models, and we have this also in remote sensing, where you describe a bit the orientation of your different shapes, right? And then you ascribe some scattering properties to this, and you trace back really individual photons or a bunch of photons hitting your target and how they are scattered, how they are absorbed to generate your scene. Then we have, as a second group, more geometrical optical models, where you assume a forest, for example, is made up of some shapes, right? The tree crowns, and then you have some shading of the tree crowns and of the ground, right? And then you model based on geometrics, which is relatively simple, but you also see it's a strong simplification. For example, the tree crowns are not completely opaque, but they are transmitting light and so on. And then we have this third bunch of models, if you like, which we call analytical models. I don't know if it's mathematically the correct term, where you use analytical formulas, therefore probably the word to describe what happens in terms of absorption, transmission, scattering inside this vegetation canopy. So it's immediately clear that we need some simplifications, because compared to the atmosphere, again, to take this example, the vegetation is extremely complex, because if I tell you, we describe usually the vegetation as a bunch of leaves, right? Having a certain leaf area and perhaps a certain thickness of the leaves, and then they have concentrations of chlorophyll and water, you would immediately say, yeah, but does the size of the leaves have no impact? There's sometimes wax layer on the leaves, or little hairs, or the upper side is different from the lower side, or, you know, I mean, if you go into detail, the more you go into detail, you see how much we simplify this to make it handleable. So, but the downstream is also clear. If you don't simplify, right, for your downstream application, you have another problem, because you will end up with too many unknowns, because most part we want to do inference using these models. So if you have hundreds of unknowns, but you have only 10 spectral bands, right, you are also doomed somehow, because you can't solve this problem. So we need this simplification in terms of our limited process understanding on one hand, but then also as a need for ensuring a kind of usability. And I cannot stress enough how important was the year 1992 in this respect, because that was the time when the so-called prospect model was developed, which links the optical properties of individual leaves across spectral bands. You know, because if you think, I have in a Sentinel-2 satellite, I have perhaps 10 spectral bands. Now, if you have then a bunch of unknowns, it helps you if you can simulate the reflectance properties across the spectral bands, not individually, but simultaneously. For example, by using a kind of, if you have a chlorophyll concentration, right? And the chlorophyll concentration is a physical or biophysical quantity. which shapes all the bands. And if you can develop this kind of linkage between bands, right, then you can simultaneously invert this model over all the spectral bands.
Was it developed empirically, or
say it again?
Was it developed empirically through observations, or was there a model for it? How was it done, the prospect?
Yeah, it was calibrated. Let's say there's also a physics. It's also part of a radiative transfer model, limited only to the optical properties of leaves, so describing reflectance, absorption, and transmission. And then they measured, I don't know, several hundreds of leaves having many different concentrations of chlorophyll, other pigments, water, leaf structure, and then they calibrated so-called wavelength-specific absorption coefficients for these absorbers, if you like we would do for the atmosphere. Ozone, for example, as an example, you can wavelengths per wavelengths measure and quantify and then fix the absorption coefficient of this gas, right? And you can do the same for chlorophyll and for water. So that once you have fixed these absorption coefficients, then by changing the chlorophyll content, right, you modify all the bands at the same time. So that was more a kind of combined lab study and then some physical modeling.
So given this, do they then specialize it per species distributions to say that this is the chlorophyll?
Yeah, no, not per species, because the idea would be we want to be species agnostic. So a chlorophyll is thought of a kind of molecule which is unique and which is exactly the same across species. I guess it's also true. Not sure. The concentrations will change and the covariation with other pigments will change. But the chlorophyll, I saw once the formula in a kind of textbook, and my wife had to learn it by heart and reproduce it for her exam in France. So this is a fixed molecule. So which has then fixed physical properties in terms of how much light is absorbed. No, we try to always ignore what is species dependent, to have models and ways of using these models across species, across spatial areas and geographies and so on. So just to remind you, when I talk about radiative transfer models, you can in principle have them at every scale. You could have them at microscopic scale. When I'm talking about, I think about a pixel the size of this room, right? Where you have, let's say, 10 by 10 meter or something like this. So in terms of applications, I will go and show you a bit for what is it useful. And this ranges from really simple sensitivity analysis to some digital twins. Before doing, let me briefly provide you a kind of history, which is closely linked to this guy. So he's not French, he's from the Netherlands. Verhoef, yeah, Wout Verhoef. So he's now emeritus professor of radiative transfer, you see. So he worked his whole life on this kind of models. And you see also it's quite old because it's from the 1974. So that is probably where most of you were not even born, right? So that shows it has been a long time around. So in the first model, I think because of the mathematics, they assume the canopy has just a mix of vertical leaves or horizontal leaves. You see the simplification. There was no leaf in between. Either it was horizontal or vertical in different amounts. So then the second step was then almost 10 years later, the Sale model, which had then a complete leaf angle distribution. And then again, a couple of years later, they model also the hotspot effect. What is the hotspot effect? Is if you look, for example, at the vegetation canopy, but it also for soils, and the sun is directly behind you, yeah, you see no shades. And if you turn around, you see the same soil or the same vegetation canopy much darker because now you see the shade. So this is what we call the hotspot model. And later they did something like these geometrical optical models for forests. Now here, these are the guys which, in my opinion, they deserve the kind of Nobel Prize in remote sensing. Because this Fred Barré, he was the PhD supervisor of this Stéphane Jacquemus, and they developed these leaf optical models, which for the first time was able to simulate the full spectrum from 400 nanometers to 2,500 nanometers based on a few variables like water content, chlorophyll content, and so on. And at this time, I was in Avignon. I was just a student, and I was just looking for an internship. But I had no French knowledge. I could only say oui and non and je t'aime. So then I was running around and I was asking the farmers, please, can I help you collecting fruits? But they had no need of me because probably I was a student and not made for hard labor. But then I came to this institute, just walking around. And they had a kind of a student who became later professor that nobody wanted to work with. And they thought, okay, then we will put little Clement and help her doing the field measurements in rice. So we had to go into the rice fields. We had a radiometer measuring the incoming light and the reflected light. And then we had to cut the rice, and bring it home and do the lab measurements and so on. So then I came into this group and I learned about this. So, and then I use this kind of concepts then for kind of forest models that Jiang is using later on. So if you see a radiative transfer model, you can simplify it like here. You have in fact incoming light, and part of this is transmitted through the canopy, but part is also scattered, and on the way back you have the same part is directly transmitted, partly is transmitted, let's say, as a diffuse radiation. And because there are these four streams, we call these four stream models, and most of the models are based on this. Now, the advantages is you don't really need field data because there's no more calibration step involved. You can use all your field data just for validation. In principle, if you describe the physics well, you have a kind of generic model which you can apply everywhere. So it's really scalable. You can use the same model with different kind of sensors. Whereas usually if you do a work completely empirical, you have to develop your model for TM sensor and then for the Sentinel. Here you can, in principle, combine and blend all kind of sensors. Okay, and we describe these four streams. Now, this is one major simplification by leaf layer. So a canopy is thought out of leaf layers. Let's say a leaf area index of 1 means you have 1 square meter of leaves per square meter of ground. Okay, and then if you have a leaf area index of 3, right, you have three of these layers. And inside of each layer, you do these calculations, and then the part which is transmitted to the upper leaf layer goes into the second leaf layer and so on until it hits the ground, and then you calculate it backwards. So some applications, as I thought, we use these for our students because we have a kind of, I don't have it here, but we have a kind of, I think you saw it on QGIS, no, a kind of graphical user interface where you can change parameter values and then you see what happens in terms of reflectance properties. And I think it's very intuitive. And it helps you to understand, let's say, the relation between variables. For example, you see that I mean, we know this, that the red reflectance saturates very quickly if you increase the density of your canopy, whereas the near-infrared remains sensitive, right? You see also that we have a strong impact of soil brightness, right? So if you have a given leaf area index, but your soil is darker or brighter, it changes drastically your reflectance that you measure. And you can simulate here in a simple way and understand until which density of your vegetation canopy you will have which sensitivity to soil brightness changes, something like this. Or here you see how the reflectance spectra changes if you increase the leaf area index. For example, most students, if I tell them, okay, we have a green canopy, and so it's green, and now you increase the density of the canopy, so you add additional green layers. What will happen with the green reflectance? So the green reflectance is roughly here at 550 nanometers, right? And most students, almost all, say, yeah, if I increase the leaf area index, the green reflectance should go up. So, and then if they play around, they will see, oh no, it's exactly the opposite way around. It becomes a darker green. Yeah, it becomes a darker green because it's more absorbing, right? So for learning purposes, it's very nice. Here, perhaps something on the average leaf angle, where you immediately see if your leaves are more oriented vertically, you have a stronger transmittance through the canopy, and this will then automatically also affect your reflectance signature, and how much is affected you see here. Okay, that is perhaps on the sensitivity analysis. Then for sensor design, that is perhaps not that important for you, but I mean, often we might be asked, okay, what would be an optimum sensor for either a field device? Imagine you want to develop a field device, or a satellite sensor, or something in between. And if you run these radiative transfer models, you immediately see which spectral bands are most affected by which of these many variables. So, for example, if I had only one band and I want to estimate, I don't know, leaf area index, which is shown here as yellow, and I want to be minimally affected by changes in leaf angle. So leaf angle is perhaps something which is very much crop type specific, right? You have crops which have more horizontal leaves, you have other crops with more vertical leaves, right? I would not go for the 1000 area, 1000 nanometer, because here the red, there's a huge sensitivity to these leaf angle changes. Something like this you can think about. Or if you want to measure proteins, right, which have only absorption bands in this sphere region, so around 1700 and perhaps 2200, right, you see, okay, taking into account that I have a strong impact of the leaf water content, right, there's no hope to get it correctly. Perhaps I better look at the indirect correlation between protein content and chlorophyll, because the chlorophyll is unaffected by water content. So these kind of considerations you can take into account. Now, Maddie is here. Nice picture. One major area of research is obviously how to design, let's say, good retrieval algorithms. And Maddie, but also Joshua in my team, they work on what we call the Barlow twin. We now renamed it into the spectral temporal Barlow twin, right? Where the input is on the left-hand side, a kind of corrupted spectral temporal signature. So just to make it clear, in the columns we have the 10 spectral bands of Sentinel, and each row is one 5-day period. So we have 73 not decades, how do you say? Pentates? No.
Transits.
Hmm?
Transits.
5-day periods.
5-day period, yeah.
So, but part of them, and they are shown here as white, are cloudy. There are many more which are cloudy. Okay, so this would be here a nice case because most are not clouded. So imagine there are many which are missing. So what we do is kind of data augmentation, meaning we take 10 random temporal samplings and do this twice or many times. So we have this upper part and the lower part. And then using this Barlow twin, we make sure that on the cross correlation matrix that we get out at the end, you know, the diagonal is full of ones, so meaning they are highly correlated, and all what is off diagonal is black, so no correlation between the different latent variables. Now, what is the relation to radiative transfer model? What we get out now in terms of representation has no physical meaning, just some latent variables. And we use them for downstream applications like the crop classification and so on. So, but our next step should and would and will be to replace the empirical data that we use right now, so the observed data, by simulated data. Because if I can input this lower part, so this what we call the D pixel, which is generated using a radiative transfer model, then I know which parameter setting of the radiative transfer model gave me this input, and then we can link the latent variables to those inputs. Then we know, okay, the latent, they don't become physical, the latents don't become physical, but we can link them and explain them as a function of the biophysical variables. So that would be one application. So main application of radiative transfer models is, of course, let's say the inverse modeling, so or inference, where we want to make these kind of nice maps. Just leaf chlorophyll content and leaf area index. And you see here on these results that it's absolutely positive, and it avoids a bit what we do in a classical way. In a classical way, you would go down in the field and you would take one of these devices, which is shown on the button, which measures the transmittance in different angles. And then because the angles matter, from the transmittance, these 5 angles, you calculate the LAI in the field. So you take one measurement above the canopy, another under the canopy, and then the program calculates the LAI of your crop, for example. But then you have only one point, right? So you need many points to make it replicable and to make it stable, and then you need to make sure that you have a kind of variability in your area, and then you regress it somehow against the NDVI. Something like this is perhaps the classical way, but you see it's costly, it costs time and money, and you need to redo it every time. And it's the same if you replace an NDVI by something more performant, I would say, like a PLS regression, right? Still the same. You always rely on empirical data. So, but you can, if you have a good, and it's really important to say, if you have a good radiative transfer model, you can skip all this and just do inference by using one of several techniques. So I don't think that this is anymore used, but this is how we started when we were using MATLAB to do it, because we had these numerical optimizations, right? So you have your radiative transfer model. You start with some initial guess of your biophysical variables. You get some model spectrum, and then you compare your model spectrum against the observed spectrum. There will be a mismatch, and this mismatch is linked back to the parameter space, and then in the second iteration you get a better estimate, hopefully. I mean, this is the same way we do learning today, right? But here it's applied pixel by pixel, and therefore it's not that good because you need to repeat this again and again and again. So if you have billions of pixels, it doesn't scale well. So then people came up very quickly with these ideas of using lookup tables. So why not directly simulating 1 million spectra, storing the simulated spectra in a table together with the associated biophysical variables. And now I take my first pixel and I look in the lookup table, where do I have a good match? And then this pixel together with the associated biophysical variables becomes my solution, and you can expand this and get also some uncertainties around this. But nowadays, most people use kind of neural net, of course, and that is the linkage here to our work, probably just to learn the mapping from the reflectance space to the parameter space, because I think there's this argument of speed, right, and computationally, and it's very, very efficient, and you can estimate several of these vegetation traits simultaneously, and so on. And how does it look like? This is now for forests. These are needle leaves. So this is the problem, right? If you have a model which has been developed for conifers, you can't apply it to broadleaf forests, and vice versa. So therefore here you see a bunch of colors, but you see also a lot of gray, and the gray is all what is not in your model domain, right? So there we don't even try to estimate these biophysical variables, but we say, okay, the model was not developed for this kind of canopy.
And you just use out-of-band data sets to do the masking there?
Yes, exactly. Either you have kind of GIS data set and you know where you have this, or you do first a kind of classification, right? The alternative way is, I will talk about this a couple of minutes later, is a kind of outlier detection. If you have your model for your spruce forest and you have ideas of the plausible parameter range, you can simulate also plausible ranges of your reflectance values and the covariation between reflectance bands. And now if you have a pixel and you're not sure is it in the domain or not, you can simply look if it's within the distribution of your simulated reflectance values. This is a way to check this. So here's the same for, I think these are beech forests, where you see that we can derive good maps of these characteristics. Of course, here we did some verification, so we went to the field, but this is also a shortcoming of, you know, especially when working with geotree, people always say, what is about the quality of this? And they tend to believe that field measurements is always the best. But I have been in these forests. The first question is, which leaf do you sample? Do you climb to the top of the tree? Do you take a leaf in the middle, or all this? So it's, what I want to say is, it's very difficult to verify and to validate these kind of models, because it's extremely difficult to measure these quantities in the field also. So okay, I think we can discuss about this. I think you talked about this control plot selection. What we do in geotree is, for example, if we have these degraded grasslands, in the top image you see a bunch of fields, right? These are our project fields. And now we want to identify in a radius of 100 kilometer which other fields we can use as counterfactuals, so as controls. And we want to make sure that the fields that we identify as controls were similar to these fields over the past 5 years, for example. Now, if you think about an area of 100 or a radius of 100 kilometer, and you have 5 years of data, you don't have clean images. You have an image here and there, and then it's partly clouded here and there. So what we do is we train an autoencoder which takes from the project pixels or from the project plots the reflectance signatures whenever they are available, plus a timestamp, which is the day of the year, but coded as sine and cosine. So this autoencoder learns the project pixel spectral signature in the year, during the season. I don't know if it's clear now. He has kind of knowledge then of what spectral signature is plausible for a given day of the year. Now, and then we score each other pixel, and he will see, okay, perhaps this signature looks the same as the pasture, but not at this point of time, not during winter. Perhaps during summer it would be good, but during winter it doesn't fit. So because you said, I think you alluded to this with the problem. This way we can easily score, and you see here a result. We can easily score all our pixels and find now pixels or units which can which have low reconstruction error all the time. All the time.
It's using RTM. I mean, this idea is very good, but there's no RTM in it.
Yes, but now you could think about how to make use of the RTM here.
Yes, I can. Yeah.
So, and that is a bit what I wanted to show, that we could replace, let's say, empirical data again by some synthetic data and find and define the autoencoder based on this synthetic data. So we would not need again this empirical data.
Do you find if they're similar, are you looking at distance in the embedding space?
No, in similarity, it would here be defined between the input data, which are the spectral signatures at input, and the output, the reconstructed spectra. So kind of Euclidean distance from the input spectra to the output spectra.
So for the control and treatment, you will look at the input and output spectra and not the code?
No, the code is not used here at all. Okay. The idea is the encoder weights and the decoder weights are once trained and fixed. So they learn the spectral temporal behavior of your project pixels. Then it's frozen, fixed. Now you score all pixels in this autoencoder. And if it comes from a similar distribution, it will be well reconstructed. But if it's out of distribution, it will not be well reconstructed. So this is a lot used in industry, to detect outliers. Because in industry, often you have this application that you have a bunch of good material, but you don't have, let's say, the defect material, the outliers. You don't have all possible things that can happen in your industrial procedure. So you learn only the good behavior.
Yeah, that's not good as bad.
Yeah.
So, I think that makes sense, right? Excellent, thank you.
Okay, I come to my last point. It's a kind of what we call digital twin. It's a kind of name which is used by many. So the idea is how to make better use of process models. If you want to simulate something like carbon sequestration, you can, of course, measure, let's say, somehow, but often we rely on models which simulate a bit how plants grow. Yeah, there's incoming light. You have already some leaves. They absorb some of the light. They convert it into dry matter. They store it, partly some part is used for building new leaves and so on. So these are dynamic process models. You have to imagine they run on a daily time step often. So they take the light and build and grow, right? Now it's they are parameter rich. So there are many unknowns, soil composition and so on. So they are doing well if you have really a bunch of good measurements, so for experimental sites. But if you want to apply them for tropical forest, usually you don't have all the inputs that you need. So what can be done, of course, is to use reflectance data from satellite, for example. And one approach is, this is not my favorite one, is to convert the reflectance measurement that we observe into some of the state variables of these models. For example, one important state variable is the leaf area index. So how many leaves do you have? Because they will determine the interception of the light, but they also impact, I don't know, transpiration, evapotranspiration, and so on. So you force it into the model, as shown here. I don't know if it's clear. So you somehow force the remote sensing data into your dynamic process model. The other way, it's also not my favorite, is to these crop models or these process models. As I said, they model the daily evolution of all these state variables, and LAI is one of the state variables. Now, if you use your reflectance data from satellite and you get your LAI, you can compare your observed LAI against the model LAI. So, and then you fine tune some of the parameters so that you minimize the match between observed LAI and modeled LAI. But what I call digital twin avoids this completely. So the idea is really to take the output of your dynamic process model, and one output is, for example, the leaf area index or the nitrogen content, and you ingest this into your canopy reflectance model, so into your radiative transfer model, and then you simulate the spectral signature. So now you have a model which simulates you how the pixel changes its reflectance day over day. And now whenever a satellite comes, you can compare your satellite reflectance spectra against the simulated spectra and then fine tune some of the model parameters. A bit like here. So this is based on latent variables. So there's no process model behind, but you see there's a daily simulation of the reflectance pattern. It changes only slowly because it goes from March to August, I think, in France. Now you see a lot of change. Imagine you had a process model spatially distributed, many billions of pixels simulating for each pixel this reflectance behavior, and now you have an observation. Whenever it is and whatever sensor it is you have, you can combine all these sensors and recalibrate your model. Okay, this is a dream. So to summarize, I think radiative transfer models are very helpful, and I think the linkage to machine learning and AI is clear. I did not talk about ill-posedness. Perhaps in the discussion we can talk about this. For me, it's important that in remote sensing we move away from this use of vegetation indices. And radiative transfer models are really well done for this because anyhow they simulate the full spectra. So during inference you can also make use of all these wavelengths at the same time. And yeah, in addition, we should also consider the spatial dimension. Of course, I have some more slides, but as time is limited, I stop here and I thank you for your attention. Thank you.
Thank you. Okay, we have time for questions. Yeah, Rodian.
Thank you for the talk. So I wonder how applicable is info or other models in the Artian family to the tropical forests? When you develop the models, do you consider like the geometric shape and species in tropical forests?
Yeah, most people avoid developing radiative transfer models for forest altogether, and even for our kind of well-managed forests, because the complexity compared to agricultural crops is a magnitude higher probably. Because as you know, an agricultural crop, this is all genetically the same material. Your field is all maize, right? It's the same cultivar, sown at the same date, treated equally. So that is just one plant species. And then the more you go into, let's say, natural forest, tropical forest, the more you tend to violate the basic assumptions of these radiative transfer models, because they need to do some simplifications. For example, what is tree height, right? Now, we know in tropical, or I don't know, but you probably know in tropical forests, there's no real tree height, but you have many tree heights intertwined, several types of stories. We can model this, but it becomes more and more complicated. So yeah, with your approach, we try a bit to make at least partly use of the physical knowledge which is encoded in the radiative transfer model, and to have in addition a kind of additional layer which corrects, for example, for local differences to real forest. So this is a bit what we try.
Great. It's on because it's from Evening, so let's go to that. Evening, can you just unmute, please?
Yes. Hi. Thank you for a very interesting talk. So I had a question which is probably related to the last one. It's also about in forests. I was wondering how the spectral signals could be related in addition to LAI, but also to like the vertical distribution of LAI, which could be an indicative of forest canopy structure.
Yeah, I mean, we have not for forest canopies, but for example, for agricultural canopies, we have radiative transfer models, which, for example, do not assume a vertical constant value of leaf water content or leaf chlorophyll concentration, but you can think about a gradient, so that the top leaves have more chlorophyll and then you have a kind of gradient going down. So this is just one more equation describing, okay, it's not constant, but somehow kind of function of height, right? And this you can always incorporate, and we call this multi-layer radiative transfer models. The principle is simple. You take your first layer, right, and it simulates the transmission. If you want to simulate the reflectance, you need automatically to model well the absorption in this canopy and the transmittance. So if you simulate your first leaf layer, or first meter, if you think, the transmission here is the input of your second leaf layer. So what I want to say is you can easily stack them. And this is what I did, for example, in Inform. I have an upper overstory, which are my trees, and then I have a lower understory vegetation canopy, which receives as input the transmitted light from above, and then it goes back the way up again.
How do you decide how many layers you need?
You can add as many as you want, and there you can associate different properties to each of these layers. So you could say, okay, I have different type of leaf optical or leaf chemical properties in the top layer, and then I have a gradient, so it's a bit less here, a little bit less here. So you can easily stack them.
Thank you. That was very helpful.
Okay.
Thank you, David.
Thanks so much for your talk. I mean, I come from an ecology background, and then 15 years ago, the government had a lovely plane with LiDAR and hyperspectral in it, which they were just begging people to use. So that, and I had opportunities to go to tropical forests. I've actually sort of avoided ever having to think too much about canopy level RTMs. We've always just thrown our atmospheric corrections sorted out using RTMs. But so you've answered. Thank you. You've already answered some of my thoughts. The other one was just about the sort of range of leaf properties that we're interested in as tropical biologists, and how they map onto what are sort of currently available in the sort of toolkit for crops. So nitrogen, water content, chlorophyll content, protein content. Those ones are seem to be relatively available, but things like anything to do with the secondary compounds, the terpenoids and the and the other chemical compounds which are very closely related to herbivores and to soil chemistry and all those things, which we really want to know about. There doesn't seem to be a toolkit for sort of assessing those using RTMs, and I wonder whether that was just going to always be impossible, or whether there was opportunities to develop.
Yeah, thanks, David. I think that there's a lot of opportunity because the base model, the prospect model since 1992 has also evolved because the physics remain the same and people added, okay, I want to also simulate, I don't know how to pronounce, carotenoids, or I want to also simulate the effects of some other pigments. So the principle is the same and you need just field data, lab data in this case, right, where you have your leaf samples and you specify which additional, let's say, parameters you want to simulate, then we could do this. We could do this indeed, and people are doing this. So if there's a mismatch between, let's say, because the original prospect was developed over European species. So in the tropics, there are different species and perhaps different, let's say, biochemicals are more important. So we could do this together. So I don't see any fundamental fundamental reason why this can't be done. Also, the radiative transfer models evolve. I'm working with Felipe here to not only simulate the reflectance properties, but imagine that we simulate at the same time the waveform of the LiDAR. This will be his work, right? Because it's the same structural components which shape the reflectance properties, which also shape the LiDAR signal. So kind of linkage to the GDI stuff, right, where we get waveforms. So we would simulate at the same time reflectance properties and this waveform, meaning if we have the two observations, then we reduce what I call the ill-posedness of the inverse problem.
So you touched on this a little bit before. But how do you deal with seasonality? So would you have like different radiative transfer models for different stages? Or I guess at some point you can just vary the parameters for the same kind of height.
Yeah, it's very good. Therefore, I'm here. I mean, I had to write a proposal why I'm here. The proposal was to have a kind of seasonal radiative transfer model, where indeed you can describe for crops. I take the example of crops because it's simpler, right? If you think about a crop, right, there is no leaves at the beginning, right? You have bare soil, and then you have a kind of increase in leaf area index. You have changes in chlorophyll and so on. For example, the shape of a leaf area index in the absence of a fire or something like this can be easily modeled using a double logistic. So you have 5 or 6 parameters describing you the shape. So I'm going to simulate, I have started already and it looks really very good, spectral and temporal signatures using radiative transfer models. And it would be a mistake to simulate each time step completely independent of the others. You need to, as we needed to link the spectral bands, we need also to link the temporal dimension, because otherwise you have always a system where you have more unknowns than knowns. So it's important to describe the temporal coherence of this, which is easy for LEI. But if I would ask you, how is the leaf water content changing over a season? I don't know. I imagine at the end of the season it goes down, but I don't know if you can model this with a kind of double logistic, because it depends also a lot on weather conditions, right? If there's stress and so on. So, but there's a clear need for a temporal version of these radiative transfer models.
You get kind of two different paths. One of them is like a fixed seasonal path where you just get based on this, like it's summer, this is what you expect. And then there is this kind of like integrated, based on the amount of sunlight, if it's less sunlight, it happens later or it happens earlier, right? You can this kind of.
Yeah, but this we would do with this. Therefore, I'm a big fan of process models. I mean, if you then go and you take into account the growing conditions, then why not using and leveraging these dynamic process models and building on top of this the radiative transfer model? So therefore.
I think I see the next crowd wants to come in, so let's thank Clement again. And I encourage you to